Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of rotational dynamics by discussing the moment of inertia of a solid and really also of a point object. This continues, obviously, the discussion that I had in the last video that I made introducing rotational dynamics. So you will recall from that video that the Newton's second law can be applied to torques. And so Newton's second law for rotations and for torques would look something like this. Sum of torques is equal to the moment of inertia times the angular acceleration. And this, of course, assumes a constant moment of inertia. So the question that we were left with is, what exactly is the moment of inertia? Or maybe how can we get this moment of inertia term? And in some sense, I did answer what it was. It basically just is a measurement of rotational inertia. So moment of inertia measures rotational inertia. That is to say, the more moment of inertia it has, the larger your moment of inertia, then the harder it is to change the object's rate of rotation, let us say. Meaning I would need to apply more torque to get the same amount of rate change of rate of rotation, or the same alpha, in other words. So in today's video, what we want to do is figure out how to determine the moment of inertia. Now, there is a simple experimental method. So experimentally, basically what we would do is this. For an object, apply a known amount of torque about an object's axis of rotation, basically a given axis, and measure what the rate of change of the object's rotation rate is. In other words, measure alpha. And so what you would end up doing is having a plot that has on one axis the alpha, the angular acceleration, and on the other axis the torque. And you'd basically should end up with a straight line, at least so long as you don't have any external factors like air resistance providing a substantial amount of torque. The line actually should go through 0, 0. My drawing skills are not apparently up to that particular task in freehanding it, so let's draw these axes correctly. Slope of this line is moment of inertia, I. So that's your experimental method for doing it. So what does that lead to theoretically? Well, in some sense, what you can do is take a point object, or something that is point-like, and apply a torque to it. So let's imagine that I have an object that's moving on a uniform circle. So here's my object. It's moving about this circle that's centered on some particular point. This would be like my axis of rotation. So here, this dot here in the center of the circle is axis of rotation. And this object has some value mass, and it has some speed v, and it's moving some distance r from the center. Let's actually make it a capital R just for variety's sake. All right, so if I want to make the object speed up, I apply a force. So we say the force applied is the mass times the acceleration, and we notice that I could also express this as a torque. Now note that the force is, of course, being assumed to simply be making the object speed up and slow down. So we could say like force tangential. There's also a centripetal force, obviously, but this right here is my tangential force. And this would be my, therefore, tangential acceleration. Now I know that the tangential acceleration, a tan, is equal to alpha times r. I also know that the torque that's going to be applied on this hypothetical object using this as a lever arm would be tau equals force tangential times the again, radius arm. It follows from these three equations by making some substitutions of ma tan for f tan and then alpha times r for a tan. It follows that the torque that's being applied to the system is m times alpha times r times r. Or in other words, tau is m r squared alpha. And if we come back to our previous, tau should be I times alpha, it follows from all that the moment of inertia for this system is everything on this side of the equation that is not an alpha. So I should look like m times r squared. Now again, this is for a point object. So this is for a point object, specifically a point object which is moving some distance r from its axis of rotation. All right, so we've determined what the sort of point object moment of inertia is. This also, by the way, works for an extended object, but with a caveat. If I have an extended object, let's say I have a wheel or something like that, well, there are different points on this wheel that have some amount of mass and some distance from the axis of rotation. So this would be like m1, r1, and maybe over here I have another piece that's moving this way. This would now be maybe mass 2, and this would be r2, and so on. Like I can fill in the whole wheel with these. And I notice that R1 and R2 are not equal to each other. Not only are they pointing in different directions, but they're actually different lengths, and that's the important thing there. So if I wanted to add up all of the moments of inertia, in some sense my total for this system, and let's actually just call this IOBJ for object, should look like the sum of all of these individual masses times all of these individual radii squared. Well, it depends upon what shape your object is. You end up getting different values for these different object or extended body moments of inertia. So what does it depend on? It depends upon the geometry of the object, and it kind of depends in a similar sense on where your moment of inertia is calculated about. In other words, what's your axis of rotation going to be? If the axis of rotation is the center of the circle, then I expect to have a different sum of mr squareds than if it is, let's say, the edge of the circle. So, maybe the whole circle is moving about a point rather than rotating about the point. Okay, well, in an algebra-based physics course, what you would do is go find a good table of values for this. In a calculus-based, you maybe would go ahead and calculate via integration, but for an algebra-based, you find a table of values. Most textbooks have such tables. Here, for example, is such a table from the OpenStax College Physics book, and it has a small variety of different geometries, and in each case it actually shows you the axis of rotation. Quite a few of these are cylinders or rods, and you'll notice that there are a variety of different axes of rotations. So these two here that are higher up are solid cylinder or disc about certain axes. This, I don't really have a cylinder, but I've got a pen here. This is maybe more like a thin rod, but on the one hand, I have an axis of rotation such that this thing is rotating like this. Oops. Where it's just turning clockwise about this axis. And then, so that is the left of the two. The right one, you have an axis through the center. That means that it is rotating more like this, through an axis through its center. And so you have slightly different values for your object depending upon what axis you choose. There's also the thin rod rotated about its center. This is more like a thin rod than a disc or cylinder. And then there's the thin rod rotated about its end point. So more like this. Okay, you have a thin ring or cylinder that's hollow. You have an annular cylinder or ring. That's something where it's partially hollowed up, but there's like some thickness to the sides, like this literal ring. Then you have the slab. You have a hoop that's rotated about an axis that is not its longitudinal axis. So this bottom one is like I have this ring that rotates this way. The top one is more like rotating this way. And then there's also the little slab. So the slab is rotated through its center. That's if you have something like this little book and it just is rotating like this. And so viewed end on, it's rotating like this through an axis through its center. Okay, so these are different values of the moment of inertia for these different objects. There's also stuff like cubes and so on. And again, you can look this stuff up on the OpenStax book, or if you're taking this course with some other book, then look it up in that book. There's actually one further point which we can make for axis of rotation, which is what would happen if I have, let's say, an object that is an extended object that is itself making an orbit about some axis of rotation that's not through one of the axes shown. Well, this is where we use what's called parallel axis theorem. So parallel axis theorem basically says that the total moment of inertia, I total, is going to be the moment of inertia that you get through this axis that's well established. So let's say this is like I, and we could call this OBJ for object with known axis. And then that plus the moment of inertia that you would get for having this thing moving about a circle of radius r. So this whole object has mass m, maybe it has radius capital R, something like that. Your I total is therefore I OBJ plus I center of mass, which is your object, sort of like its geometric moment of inertia, plus the object's mass times, whoops, this would actually be a little r squared from the center of rotation. We'll close with a pair of related examples. So we've got a solid disk of mass 4 kilograms and radius 0.25 meters. We want to know the moment of inertia about both this longitudinal axis that runs through its center and then about this other axis that is a parallel to the longitudinal axis but 1.5 meters from the disk's longitudinal axis. So in this case what we have is I is equal to the object moment of inertia. If you look it up in the table for a solid disk, this will be 1/2 times the mass times the radius squared for the object. So you're looking at 1/2 times 4.0 kilograms times 0.25 meters squared. When you multiply all those things together, what you get is 0.125 kilogram meters squared. For the second case, what we're looking for is I total is I center of mass plus I object. So that is mass times radius squared plus this I object. Again, I object is 0.125 kilogram dot meters squared. It's the number we found up here. So I total will now be 4 kilograms times 1.5 meters squared plus 0.125 kilogram dot meters squared. This gives us a total moment of inertia of 9.125 kilogram meters squared. If you want to do some practice with significant figures here, this one right here should actually round to 0.13 kilogram dot meters squared, and this one would round to 9.1, mostly because this first term is limited to the nearest tenth, whereas this term may be limited out to the nearest hundredth, and so you go with the larger place value. Alright, well that's all for today's video. So hopefully you learned something from it, and thanks for watching, and see you in the next one.